Welcome to today's video lecture covering the formation of ionic bonds. First, we need to talk about how do we actually represent ions. And again, remember, an ion is any atom that has either a positive or negative charge. Remember that ions are formed by gaining or losing electrons in the valence orbital. And remember that we do all of this for the sole purpose of achieving the octet that all atoms want and need. Remember that the octet rule is that all atoms want to have a full outermost orbital, whether it's 2 or 8 or whatever it may be. We need to fill up, do whatever we can to fill up that outermost orbital. One of the ways that we can do this is through the formation of ionic bonds. First, there are two different types of ions. The first one is our positive ion, the cation. Cations are when atoms lose electrons and have more protons than electrons. So our example is going to be potassium. Now, let's take a peek at the periodic table. Potassium is in the first column right here. Yeah. So that means that it has 1 valence electron. Everything in this column has 2, and we have 3, 4, 5, 6, 7, and then 8 are noble gases, who are all sorts of snooty because they already have 8 electrons, so they don't want to interact with any other atoms. So their octet is already achieved by themselves, because wouldn't it be silly to lose an electron just to gain it back? Now, potassium right here has an atomic number of 19. 19 means that it has 19 protons. So let's zoom in on the nucleus of this potassium atom. We're going to draw all of the 19 positively charged protons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18, 19. There we go. Now, as this atom is, it has not gained or lost any electrons. So we need to represent its 1 valence electron, and we're going to do this with a Lewis dot structure, because Lewis dot structures are designed to represent just the valence electrons. As of right now, it has 19 electrons. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 electrons. So currently the net charge, which means total, net means total, not that thing that you kick balls into, is 0. Net charge is 0. Because each of the protons cancels out an electron. Now, when we form the cation, remember cations are positively charged, we lose an electron. That, poof, for right now we're just going to say it runs away, it goes somewhere else. So now we have a positively charged ion. This K is different than this K, so we need to represent that somehow. We can't just draw a K without the dot, because people would still get confused. So let's take a look at the nucleus real quick and see what the difference between these two are. So we still have 1, 2, 3, 4, 5, 6. We still have 19 protons. Why? Because the protons are what determines the type of element that we have. Now we lost an electron, so I'm going to scratch this out. Go away. Now we have 1, 2, 3, 4. So each of these are canceling out. So our net charge is now going to be a net charge of, we'll see, and we've got 1 left, a positive 1 net charge. So now our new net, so we're going to write this in this greenish color, is new net charge of +1, because we have 1 more positively charged particle in the nucleus than negatively charged particles surrounding it. Now, in order to represent the charge or represent that this is a cation, we must put as an exponent +1. So the net charge must be written as an exponent to denote that this is a cation. Now let's do the exact same thing, except we're going to use an anion. We're going to use oxygen. Oxygen is going to form an anion. So let's see what it wants to do that. Oxygen right here, atomic number 8, means that it will have 8 protons, and it is in that 6 column, so it has 6 valence electrons. Remember, we don't want to pair them up until we have to, 5, 6. So then we've got 2 lone electrons. Inside of the nucleus, we have 8 protons. 1, 2, 3, 4, 5, 6, 7, 8. Around the nucleus, we have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now, this oxygen is not happy. It wants to have a full outer shell. So we need to take 2 electrons from somewhere. We'll talk about where those come from in just a second. But we need to take 2 electrons and add them to this. So now, down here, I'm drawing those 2 new electrons. These are the new ones. And now we have an oxygen with 1, 2, 3, 4, 5, 6, 7, 8. Perfect. 8 is great. We now have 8 electrons. Now, in order to note that this is an ion, because this is no longer the same oxygen that we were working with earlier, so we need to note that somehow. We're going to note that by jotting down the net charge. So notice, these all cancel out. All the protons and electrons cancel each other out, and we are left with 2 negative electrons at the bottom. So we're going to write a 2 minus to note that this has 2 more electrons than positive protons. Okay, now this is how we represent them. These are just going to and coming from an arbitrary location. In our bond formation section, this is what explains where these electrons come from. So we're going to start off with sodium and fluorine. So sodium, Na, on the periodic table, right here, atomic number 11, that means it has 1 valence electron. So we're going to draw its valence electron right there. There we go. And it's going to combine with fluorine, which is on the right-hand side of the periodic table. We'll write that one in purple in column number 7. Now again, remember, ionic bonds are always between a metal and a nonmetal. So we need something from the left-hand side of the periodic table to combine with something on the right-hand side. Now, in order for sodium and fluorine to both achieve their octet, look at that, isn't that just like a match made in heaven? That's beautiful, because sodium wants to get rid of 1 electron and fluorine wants to gain an electron. So if we fill a room with both sodium and fluorine, that sodium is going to want to get rid of the electron with any means necessary so that it can become happy. We don't want a sad atom, we want a happy atom. So this sodium is going to donate or transfer its electron to the fluorine. Now again, once we form our products over here, when we form our products, remember, we no longer just have a sodium atom. It now becomes a positively charged cation. Why? Because we now have 1 more proton than electron, because we gave it away. We gave away that extra electron. So we are now left with a sodium atom with 11 protons. And right now the electrons is 11. And then on the other side, we have our positively charged sodium atom. It's now an ion. It's in fact a cation because it's positively charged. So we need to note that with a +1 charge. Now that fluorine, now that it has a new electron, we're going to redraw it with that extra electron. Now this isn't the same fluorine that we had on the left. It now has an extra electron. So we need to note that somehow. So now this one, fluorine, has 9 protons. and this one has 9 electrons. And over here, this one still has 9 protons, because if we change the number of protons, we're also changing the compound that we have. And now it has 10 electrons. So this has a -1 charge. Make sure that we note all of that when we're describing the formation of these ionic bonds. We're going to do one more example because they all are not perfect just like this. Our next example, we're going to take aluminum as our cation, and then we're going to use oxygen as our anion. We're going to do that one in purple. Now, aluminum is right here on the periodic table. We see atomic number 13.
Olivia Carney, Amelia Starr.
So that means that that aluminum atom has 3 valence electrons. So I'm going to draw all 3 of them. 1, 2, 3. Next, our oxygen atom right here still has the same amount. It has 6 valence electrons right here. 2, 3, 4, 5, 6. There we go. Beautiful. Now, in order for that aluminum to lose all 3 of its electrons, we need to give it away somewhere. Now, unfortunately, that aluminum cannot give all 3 of its electrons to oxygen, because oxygen can only take 2. So this oxygen, I'm going to draw my arrows over, can take 2 of them, but then that third has to go somewhere else. Fortunately, these chemical reactions that we're using or describing with these symbols occur on the scale of millions or billions of atoms. So we're never going to actually have one aluminum atom interacting with just one oxygen atom. In fact, there's going to be millions or billions of extra aluminum atoms or millions or billions of extra oxygen atoms hanging around to work with. So we can assume that we can take another oxygen to take up that third electron. So we're going to transfer this one over here. So now that aluminum is happy. Hooray, we've got a happy aluminum. But that oxygen is sad. It's not yet octeted. It only has 1 valence electron that is unpaired. So we need to find a way to pair that up. So let's make another aluminum atom. Aluminum still has 3 valence electrons, so this one can take that one. There we go. Now this one's happy. Yay. This one's still happy. This one's happy. But now that aluminum is still sad because it doesn't have a home for its last 2 electrons. Now again, we're going to repeat the same process. We're going to draw another oxygen atom. 1, 2, 3, 4, 5, 6. And lo and behold, that gets rid of our last 2 electrons. Beautiful. So in order for aluminum to interact with oxygen, we need 2 aluminum atoms and 3 oxygen atoms. Now these are going to produce the following ions. We have in the anion list 2 aluminums. Each of these has 3 less electrons, so that means that they've got a charge of 3+.
If you are a freshman.
And then lastly, we have 3 full, happy oxygen ions with a 2- charge because all 3 of them gained 2 electrons. And beautiful, there we are. So that is Al2O3. Hopefully this helps clarify any issues that we may have. Do not be afraid to just add more of these as long as we've got extras to work with, because like I said, for the most part we're interacting with orders of magnitude of millions or billions, so we've got plenty of extras to work with.